is solubility, you might ask? Well, I'm going to tell you in this 5-minute film. Now, some people think they already have an idea of what solubility is, but do they really know what it is? What's the first thing you think of when you hear solubility? Is that where like it goes through like this? Like a slide? Others have a better idea. What's the first thing you think of when you hear solubility?
Solubility? Like the amount of like, I guess, salt that can dissolve in like water basically. So you want to say just water? Water. Straight up water. Kool-Aid. Kool-Aid.
Wow, you would be a stereotypical black person.
Kool-Aid.
Alright, what about you?
Water.
What about water?
It's the universal solvent.
Do you have anything serious to add?
I was gonna say Kool-Aid. That's the example we always give. Kool-Aid.
Kool-Aid is what?
Kool-Aid, the powder, is a solute. The water is a solvent. Together, Kool-Aid makes a solution.
Oh, you're so smart. What's the first thing you hear when you think of solubility product constant?
Wait, what? Product constant?
Solubility product constant.
Like, do you know what I'm talking about? Yeah, I do. Has to be nailed. I'm guessing you put the same kind of. Wait, are you talking about like when you like have an equal amount or whatever? Yeah. I'm probably totally wrong. Is that what you're referring to? Are you respond? I don't know yet. I don't know. My brain's still loading. Solute in there. Product constant, like the product would be Kool-Aid, and the product constant. So you'd be
You want some fried chicken with your Kool-Aid also? Good gracious!
and watermelon.
Solubility is just the ability of a solid substance to dissolve into an aqueous solution. But in addition to solubility, there is a solubility product constant. All a solubility product constant is the substance's ability to dissolve in the aqueous solution at equilibrium. It represents the level at which a solute dissolves in solution.
Solubility, you will always have a solute and a solvent. A solute is the thing that is being dissolved, and the solvent is the thing that is doing the dissolving. A lot of people know water as the universal solvent, and this is a really good thing to remember because it'll also help you identify what substances might be doing a dissolving process in other situations.
It's important to pay attention to the value that you get for your KSP because KSP is most times written in scientific notation, and scientific notation can make a number that's really small and make it look like a really big number. The higher the KSP value, the more soluble the substance is. So if in scientific notation you have an exponent that's negative and it's really, really large, that means that it's actually a really, really small number, which means it is less soluble in that substance. But if you have a negative number and it's smaller, that means it's more soluble in that substance.
Also very important to remember that solubility is not only dealing with salts, salt being NaCl. Most our all ionic compounds are called salts, but when most people think of salt, they think table salt, and this is incorrect because solubility can be measured based on the solubility of any salt.
Solubility product constant expression in the solid is never represented. The only thing that's represented in the solubility product constant are the ions of the salt. Are there any exceptions to KSP? There actually is. The common ion effect is an exception, and with the common ion effect, the solubility of the reaction is reduced by the common ion. A reaction with the common ion present has a lower KSP value, and the reaction without the ion has a greater KSP. Next for KSP is molarity. That's simply because you're measuring the concentration of the ions present in solution. Solubility is the number of moles of the solute that can be dissolved per liter of solution before the solution becomes saturated. Molar solubility can be calculated using the solubility product constant and some stoichiometry.
All you have to do to find out if your solution is saturated, undersaturated, or supersaturated is find the grams of the solute over 100 grams of water, as you see on the y-axis, and then find the temperature that the reaction is taking place at, and go over to your temperature, and then follow your grams of solute over 100 grams of water up to the solution that is being asked for in the question. If the or the plot that you find falls above the line that you're looking at, then your solution is supersaturated. If it's under, it's undersaturated, and if it's on the line, it is saturated. And KSP deals with saturated solutions, where you would put a metal in there, and you see the color that the solution will change when this metal is dissolved in it. The metal forms a precipitate in the solution. All these solutions are sodium hydroxide, aqueous, and the furthest one to the left is dark green, which is iron 2, The next one is iron 3. As you can see, it forms a different color than iron 2. Copper 2 forms that infamous blue color, and the last one is zinc, which will form a white precipitate. When essentially a double replacement reaction occurs and two ions come together to form the precipitate. So in the first test tube drawing here, you have lead 2 and nitrate to form lead 2 nitrate, and then in the second you have potassium and iodide to combine to form a potassium iodide solution. During that double replacement reaction, the lead and the iodine would react to form a precipitate, and then you're left with ions of potassium and nitrate floating in solution. Okay, so basically for parts A and B here, all you have to do is find the molar solubilities, and to do that you just take the KSP, and since the the equation for KSP is KSP equals the concentration of ions, however many concentrations of ions you have, you just raise that number to a power, or you make x raised to that number power. So for part A we had 2, so it would be x squared, and you just take the KSP and you square root it, and you get 8.7 times 10 to the negative 4th molar, and you do the same thing for B. You just do the same thing for B. And you get 5.8 times 10 to the negative 4th molar. Okay, for this next part, you're solving for the concentration of SO2, or the concentration of strontium 2 plus required for precipitation of each salt. So then you just have to compare the value of each salt, like the number of values given. So you take the KSP of strontium fluoride, and you divide it by the number of moles that's given in the problem. And that'll equal 2.0 times 10 to the negative 6, that's what the first one equals. And then the second one. Then for the second part, you do the same thing, but you do it for strontium sulfate. The strontium sulfate KSP was 7.6 times 10 to the negative 7, and you do that you're going to divide that, do the stoichiometry for that by the molarity that I gave you. And so you'll just get the same answer, or actually no, it's not the same answer, JK. You'll get y equals 7.6 times 10 to the negative 6 instead to the negative 7 molar. Since the number that we got for strontium fluoride was smaller than the number that we got for strontium sulfate, strontium fluoride will precipitate first because its value is larger. Second question asks, as a second precipitate begins to form, what percentage of the anion begins to disappear? So the second precipitate begins to form is strontium sulfate, and it appears when strontium 2 plus concentration is 7.6 times 10 to the negative 6, which is what we discovered in part C. So when strontium 2 plus equals 7.6 times 10 to the negative 6 molar, we have to find what the concentration of the anion fluoride would be. So then we just fill in the information that we know. We know the KSP, or we know the KSP values of strontium and when we're trying to find fluoride. So we plug in 7.6 times 10 to the negative 6 for the strontium, and then fluoride is our Z, and then we have to square it because there's 2 in that particular solution, or that particular substance. So then when we set that equals 7.9 times 10 to the negative 10th, so then we divide both sides by 7.6 times 10 to the negative 6, and then we square root it, and we get that Z equals 1.0 times 10 to the negative 2nd molar. We then use that to find the percent of the F minus that is in solution still. To find the percent of the fluoride ion that is still in solution, you take the concentration that we just calculated, which is 1.0 times 10 to the negative 2nd. And since there's 2 fluorides, we just double that over for the total number of fluorides, and we're going to divide that. So then we multiply by 100 to get a percent, and we get 50%.